Okay, so today we'll do a tutorial on the calculus of variations. I'll start by doing a very quick summary of the theory, and then I'll do a few examples, and then I'll let you work on the assignment and give you some hints as you go along. Okay. So let's start with maybe a few definitions. So the variation of a function y of x, so delta y, which we call the variation of y of x, is defined to be epsilon times some small function phi of x. And this allows us to build the varied function. So this delta y is the variation. And the varied function would be y plus epsilon phi of x. And we see that this leads to some properties such that if I were to do a d by dx of delta y, that is equal to epsilon phi prime of x. Alright, if I just take the derivative of the first line up here, and we call that delta y prime. So we also looked at how to find stationary values of functions. And those are given by doing delta f equals 0. And recall for the chain rule, delta of f of y would be di f by di y delta y. With a constraint, constraint would be the form of some other function equal to 0, then okay. I don't know what that was about. I guess they're having problems with their server again. Okay. Can you hear me now? I don't know what this is. This is getting really annoying. I haven't had any issues with for the past year with this thing, and then some twice already with this class. Alright. So we'll see how it goes. Hopefully this is mostly a tutorial, so it's okay for me to break in and out as you work on the problems. Of course, now is not a convenient time. So as I was saying, if you're trying to find the stationary value of a function f subject to a constraint lowercase f, then the stationary value is found by setting the variation of capital F plus lambda lowercase f equal to 0, where this lambda we call a Lagrange multiplier. And then we also looked at the case for finding the stationary values of an integral. So let's say that the integral was given by s some integral from a to b of some function L that depends on y, its derivative, and x. And so what do I mean by stationary value of an integral? I mean the function y of x such that this integral is maximal or minimal. So it's not so much a point as a particular function. Okay? So to find the stationary value of an integral, we get the Euler-Lagrange equation. And so the Euler-Lagrange equation is that d by dx of di L by di y prime minus di L by di y equals to 0. Now this simplifies sometimes. If di L by di x is equal to 0, so the L function, the integrand, doesn't explicitly depend on x. It still implicitly depends on x because it depends on y, which depends on x. But if the partial derivative with respect to x is 0, then instead of the Euler-Lagrange equation, we can use a more simple form. And the more simple form is that y prime times di L by di y prime minus L equals k, where k is the constant. And this is a more simple equation. Oops. More simple because you don't have to do that d by dx at the front. You can see how the d by dx at the front of the Euler-Lagrange equation is likely to give you y double primes. Because if L depends on y prime, when you do di L by di y prime, you're going to end up with y prime, and you have to do d by dx of that, and you're going to end up with y double prime. So typically this would be a second order differential equation. Whereas this would be typically a first order differential equation. So we also looked at the case when there were constraints. So if our constraints are given in the form of some function j of our coordinates, and potentially time equals to 0, then the Euler-Lagrange equation is modified to be, I'm using t's now instead of x as a dependent variable, so it's d by dt of di L by di qi dot minus di L by di qi. And so instead of equaling 0, that's going to be the sum from j equals 1 to k, if there are k constraint equations, of lambda j times di fj by di qi. Where the lambda j are Lagrange multipliers. And then finally, if the constraint is in the form of an integral, for example, some function dt equals some constant c, let's say. So instead of the constraint being f equals 0, the constraint is integral of f equals c. Then what you can do is build a new function L bar, where L bar is given by the original integrand L plus lambda times the integrand of the constraint, and then you can apply the Euler-Lagrange equation to L bar. Okay, so that's a summary of all the math that we need from variational calculus. So let's apply this. And so let me continue doing the example of the Batista cone, which in the problem set is problem 2.5. It's not one that you have to hand in for your assignment, but it's one that we started in class, and so we should finish. So let's do problem 2.5. So if you remember, the original idea here was that we have an x and y axis. We have 2 points. And we have an infinite amount of wire that we need to used to go from point A to point B. And we want the shape of the wire, so the wire is given by some function y of x. We want the shape of the wire so that when we have a bead that slides down the wire with no friction, the time to go from A to B is minimized. So this is an optimization problem. And so it can be solved with the techniques of the calculus of variation. So what we found in the notes, for example 2.4, we found that the time to go from A to B is given by an integral from xa to xb. In the integrand we have, or in the numerator, sorry, 1 plus y prime squared, all square rooted. And in the denominator we had a 2g ya minus y. Yeah. So the problem really is find y of x such that t is minimum. So let me just simplify t a little bit. So the only thing that matters here is finding the shape y of x, right? So the shape of the wire really is not going to depend on the value of g, or gravity. So that square root of 2g, I can move well outside of the integral. So it can be 1 over square root of 2g times the integral, and it's not going to change the answer. Similarly, the integral is going to be prettier if I choose to set the origin at A, and for the wire that I've drawn, I'm going to say y is positive in the negative direction. So this is the same as minimizing well, let's call it t prime from xa to xb, or let's say from 0 to xb actually. Let's put the origin at point A. And I write the integrand as 1 plus y prime squared square root over the square root of y. Okay, so you agree with me that it's the same problem, right? It's still going to give us the correct shape of the curve. So what this means is that we have our function L of y prime of x is equal to square root of 1 plus y prime squared divided by square root of y. So in principle, the function y is given by the Euler-Lagrange equation. So you can get y of x by solving d by dx of di L by di y prime minus di L by di y prime by di y, sorry, equals 0. And so you can do that. But we can, turns out, use a more simple solution. And that's by noting that di-L by di-X equals 0. Alright, if you look at our function L, it doesn't depend on X explicitly. It depends implicitly on X because Y depends on X. It doesn't depend explicitly. So the partial derivative of L with respect to X is 0. So that's a good thing, because that means that we can use the more simple version. And the more simple version was that y prime times di-L by di-Y prime minus L equals a constant. So what we need to plug this in, we need di-L by di-Y prime. So what we need is di by di-Y prime of L. L was equal to 1 over square root of y times square root of 1 plus y prime squared. So that's di by di-Y prime of 1 over the square root of y times square root of 1 plus y prime squared. So 1 over square root of y, as far as we're concerned here, is just a constant. So that's 1 over square root of y. And then we have d by dy prime of 1 plus y prime squared. So that's going to be 1 over 2 times the square root of 1 plus y prime squared. I'm just applying the chain rule, times the derivative of inside the square root, which is 2y prime. That means di-L by di-Y prime is 1 over square root of y times y prime over square root of 1 plus y prime squared. So let me plug that all in now to our equation, boxed equation. You can refer to it as the boxed equation. So plugging this into the boxed equation, so I have a y prime times the thing we just wrote out. Right? So I have y prime squared over square root of y times square root of 1 plus y prime squared minus L, and L was 1 over square root of y times square root of 1 plus y prime squared. And that's got to equal some constant k. Now it's just mostly math. How can we arrange this in a convenient way? I think we can factor out 1 over square root of y. And we're left with y prime squared over square root of 1 plus y prime squared minus 1 plus y prime squared equals to k. So I think we want to put this all on the same denominator. So I'm going to have a 1 over square root of y. And the thing in brackets I'm going to put on the same denominator so I can subtract them. So the common denominator is square root of 1 plus y prime squared. We'll take that out as well. And then inside I have y prime squared minus, so the second term, to put it under the denominator, over the denominator of square root of 1 plus y1 squared, I have to multiply the top and bottom by 1 plus y prime squared. That's convenient because that just squares the top there. I'm left with 1 and then minus y prime squared equals k. So the term in parentheses just turns out to be minus 1, right? So I have minus 1 over the square root of y times the square root of 1 plus y prime squared equals k. So I can square the whole thing. So then I have 1 over y times 1 plus y prime squared equals k squared. And I can write this as maybe well, let me invert it. So I have y times 1 plus y prime squared equals 1 over k squared. You can't remember, k is just some constant. All we know from the box equation is that this combination is a constant. Ultimately, what's going to determine this constant is the boundary condition on the function y of x, and the boundary condition is that the function must go through the points a and b. So once you've solved the differential equation for the function y of x, then you can set, at a, xa, you plug it in and you get ya, and same for point b. So that's what will determine the constant. There's going to be two constants of integration, right? Because this is, you have the constant k, and then you have another constant of integration when you solve for y prime. So you have two constants, but you have two constraints, because the function has to go through 2 points, and so you'll be able to solve the problem. Okay, so then 1 over k squared, since that's just a constant, then we just call that the new constant c. And so if you want to write this as a differential equation, you can write it as y times 1 plus dy by dx squared equals c. And then a lot of these problems end up like this, where you end up with a differential equation that you don't really want to solve, or it's more a subject of math than physics. So I'm not so interested in how you solve this particular differential equation. Okay. So you can look up solution. Or solve with the computer. Turns out there is no closed form for that particular solution. And the solution is what's called a cycloid. So you end up with some parametric equation of some angle theta that gives you both y and x. So you can get closed form parametric solution. So that'll be something like y of theta and x of theta. And the theta is the parameter. But that part's really not so interesting. I mean, that's something you can ask a computer or a mathematician to solve. Not so much physics. Okay. So I'm more interested in how you get to the differential equation than anything else. Alright, so what if the length of wire is fixed? So you have your problem. My computer's a bit too crazy. So again, you have your points A and B. You need to find a wire. And now you don't have an infinite amount of wire for the bead. So let's say the length of the wire, I guess I shouldn't call it L. Let's call it D. So what that means is that the length of the wire, if it's fixed, that means the integral from A to B of ds is equal to D. So it's still the same functional that we need to minimize. So we still need, so we still want minimum value of the integral from xa, we said from 0 to xb, of square root of 1 plus y prime squared over square root of y dx, but subject to the integral of ds equals d. So recall, first of all, ds, we need to write that in terms of y and y prime. So we had a trick in the notes in example 2.4. So ds is the square root of dx squared plus dy squared. And if I divide everything by dx squared inside of the square root and take out the dx squared, I have 1 plus dy over dx squared dx. And that, of course, is the square root of 1 plus y prime squared dx. So our constraint equation is like saying the integral from a to b of square root of 1 plus y prime squared dx is equal to 0. So what we do in this situation, we build a new functional which is given by the original one plus lambda times f. So in this case, L was equal to square root of 1 plus y prime squared over square root of y. And f was equal to simply 1 plus y prime squared. So thus, we want stationary value of the integral from 0 to xb of L, which was square root of 1 plus y prime squared over square root of y times plus lambda times f. If I factor it, both the f and L have a square root of 1 plus y prime squared, so I'll just factor that out. And then, so the L term had a 1 over square root of y, and then the f term had a lambda times 1. Alright, so this thing here is L bar. So again, I could apply the Euler-Lagrange equation to L bar, but L bar doesn't depend on x. So it's much easier for me to use the other version. So for the other version, we can use the fact that y prime times di L by di y prime minus L equals 0, L equals a constant. So we need again di L by di y prime. So di L by di y prime, or di L bar, sorry, just put the L bars here to be consistent. So L bar is the term in parentheses that doesn't have any y primes in it, times the square root, which has the y prime in it. So if I do di L by di y prime, the term in parentheses just stays the same, so that's 1 over square root of y lambda. And then I have again my derivative di by di y prime of the square root of 1 plus y prime squared. And that's equal to the term in parentheses lambda. And then di by di y prime is of the square root is the same as we had before, and so that gave us y prime over square root of 1 plus y prime squared. So I plug that into our equations. I have y prime times the di L bar by di y prime, so I have the first term will be 1 over square root of y plus lambda. Then I have y prime times that part, is y prime squared, over square root of 1 plus y prime squared. And then it's minus L bar. L bar had a 1 over square root of y plus lambda times square root of 1 plus y prime squared, and that's got to equal to k. Okay, so now we do the same math as before, basically. So let me factor out the 1 over square root of y plus lambda, since both terms have it. And then in the middle, I'm left with y prime squared over the square root of 1 plus y prime squared minus square root of 1 plus y prime squared. So if I put everything on the same denominator, and factor that denominator out, the denominator is 1 plus y prime squared square root, and I'm left with y prime squared minus 1 minus y prime squared equals to k. So the y prime squares cancel, and I have a minus 1. And one can arrange this slightly if you prefer. We can square it and invert it. So if I square it and invert it, I have 1 plus y prime squared divided by 1 over the square root of y plus lambda squared, and that's equal to 1 over k squared. I can just call c. And so again, it's complicated to solve. But once the computer has solved it for you, you use the conditions of y at xa equals ya, y at xb equals yb. In this case, you're going to have 3 constants that you have to solve, right? You have c, which is the 1 over k squared. And you have lambda, and you end up with an additional constant of integration because of the differential equation has a y prime in it. So first order differential equation, when you solve it, gives you 1 constant of integration. Right? So use the 2 conditions that the wire has to pass through the point, plus the condition that the integral of df is equal to the total length of wire. And this allows you to solve for c lambda plus the last constant of integration. Well, indeed, it's not super satisfying that we can't get a closed solution as a nice function. It turns out a lot of these problems end up with complicated functions. So there is one where it is possible to solve the solution. Oh, is there any questions about this, actually, first? Alright, so let me do another example where you can actually get a closed form solution. And that would be example 2.7. So anyway, problem 2.7. What program should we use to solve this? Okay. So I know at USD, for sure the students have access to Maple in the computer lab. Now I'm not sure what you have at the other institutions, but I assume that if you don't have Maple, you must have access to MATLAB if you go to the computers there. You can also use Wolfram Alpha online. It will solve the differential equations. And then more generally, if you Google the calculus of variations, there's only a finite set of examples that you'll find that are tractable. And so they're actually usually worked out online as well. So I mean, I could just regurgitate the online answers for you, but I don't think the math is so interesting. So I would use whatever's available in the computer lab, and I would use Wolfram Alpha as a first try, since that's super easy to use and free. So problem 2.7. You have a plane, and again you have our 2 points A and B. And the question is, what is the curve that minimizes the distance between A and B? So you know that it's a straight line, but prove it. So we want y of x that minimizes the distance from A to B. So let me give you maybe 5 minutes or so to have a go at it. See if you can set up the problem. So I realize you have no interest in doing this because it's not one of the problems on the assignment, but I think it will help you with the ones on the assignment. I would suggest you go ahead and try it. So I'll give you 5 minutes, and it's somewhat facilitated by the fact that you know what the answer should be. Okay, so let's do problem 2.7. So we want the y of x that minimizes the distance from A to B. So we have to set this up as an integral of which we want to find the stationary value. So the total distance from A to B is going to be the integral of ds simply. Where ds is a little line element, plus the sum of all the ds's that follow the function y of x. So we've already seen that we can write this as the integral from, say, xa to xb. And the ds we can write as 1 plus y prime squared dx. Okay, so what we really want, so we want minimal value of this. So that means our function L is square root of 1 plus y prime squared. So that's pretty much it for setting up the problem. The rest now is applying the recipe for solving it. So we notice here that di-L by di-X is equal to 0, and so we can use y prime times di-L by di-Y prime minus di-L, minus L, sorry, equals 0. Equals constant. So plugging that in, I have y prime, and then I have my usual derivative of the square root of 1 plus y by 1 plus y prime squared. That seems to come up a lot, right? So we know the derivative of that is y prime over the square root, and that's going to be minus L, which is simply 1 plus y prime squared. And that's got to equal a constant k. So again, let me put everything over the same denominator. So I have 1 over square root of 1 plus y prime squared. The first term I have a y prime squared minus 1 minus y prime squared. Alright, so then the y prime squared is cancelled, and I'm left with minus 1 over the square root equals k. So let me square that. Now I have 1 over 1 plus y prime squared equals k squared. Or let me invert that and say that 1 plus y prime squared equals 1 over k squared. Now k is some undetermined constant. Let me just call that a. Since 1 over k squared is constant, so is a. I mean, since k is constant, so is 1 over k squared. And since we haven't determined it yet, let's just call it something else. And so what that gives me is that y prime is equal to the square root of of a minus 1. Now again, a is a constant, and so a minus 1 is a constant, so the square root of a minus 1. So let's say let's call that something else. Square root of a minus 1, let's call that m. And so now I have y primes equals m. So if you want to write that out as dy by dx equals m. So now you can see where this is going. Dy by dx equals a constant is trivial to integrate, and so you get y equals mx plus b. M and b are two constants of integration. And hopefully you know how to find them. You can obviously find the straight line that goes through 2 points by setting y at x equals a, dy a, and y at x b, or dy. And so there we've proved that the curve between 2 points, that's the shortest distance, is indeed a straight line. And there's another problem in the notes there. It's the same question, but prove that, or at least obtain the differential equation that minimizes the distance between 2 points on the surface of a sphere. And so that will again give you a differential equation that's not super obvious to solve. But if you do solve it and you reparameterize it, you'll eventually find out that it corresponds to a great circle. That is, the shortest distance between 2 points on a sphere is along a line that's traced out by the plane that goes through the 2 points and the center of the circle of the sphere. Any questions about that? So I'll let you work on the assignment, and then I'll give you some help with problem 2.9. But I'll let you work on the assignment for a while on yourselves, and of course ask me questions if you have any. Let me just comment, the first problem, which is problem 2.1, you can set it up by hand, but you'll need a computer to solve it, and you can solve it online with Wolfram Alpha, but eventually you're going to end up with n equations and n unknowns, and the problem is that the equations aren't linear, they're quadratic, and so the solutions are a bit messy. Problem 3 and 4. Problem 3 was sketched in the notes. So both of these problems are a matter of reading the derivations in the notes and going through them. And that's something I'm going to let you do on your own time. And then problem 2.9 is a more similar physics problem to the example that we just did. And those problems end up with not an easy solution either. Alright, so let's give some hints on problem 2.1. I hope that you've had time to get started on that. So let me just help you set it up. So problem 2.1 is you need to find the highest point on a surface. So the surface is given by the equation of z as a function of x and y equals x squared y plus x times y. And so we want the maximum of z that lies on a circle. And so we're told that the equation of the circle is centered at x equals 2 and y equals 3 and has a radius of 5. So the equation of the circle would be x minus 2 squared plus y minus 3 squared equals 25, right? So this is the constraint equation, and so we want to write that as something equal to 0. So of course that's trivial. We just write it as x minus 2 squared plus y minus 3 squared minus 25 equals 0. Alright, so this is top one, the z is like capital F, and this one is like lowercase f. And so you solve this by building f bar, which is capital F plus lambda lowercase f. So maybe let's call that z bar. So that's going to be z, which is x squared y plus xy, and then plus lambda times our constraint equation, which is x minus 2 squared plus y minus 3 squared minus 25. Okay. And now the stationary points are given by searching for the stationary points of z bar instead of z. So you need to do d z bar, or di z bar by di x equals to 0. That's one equation. You have di z bar by di y equals to 0. That's the second equation. And then remember, you still have f equals to 0. And so that's three equations, three unknowns. And the three unknowns, of course, lambda, x, and y. And to solve these, I recommend you use a computer. And I'll note, you may get more than one solution. That's not so surprising, right? Because you have an x squared, like you have several squares, right? You have an x squared in the constraint equation, and you have an x squared in the original z. So a quadratic is going to have more than one solution. So in this case, I think you end up with 6 possible solutions. And so then you're not going to know if they're maxima or minima. So you'll have to test it. So test to find the one that maximizes z. Alright, so I'll give you maybe 10 more minutes, and then I'll help you work out problem 2.9 part A. So I suggest that you leave problem 2.3 and 2.4 to work on yourselves, because you're going to have to go and reread the notes to do them properly, I assume. But problem 2.9, I'll help you start part A. Okay? Alright, let's have a quick look at problem 2.9. This is another of the typical calculus of variation problems. So problem 2.9, part A, we're asked to find the shape of a curve for a surface of revolution that minimizes the total surface area. So we have a coordinate system. I almost guarantee that this figure will be horrible. Y and X, and we then have 2 points. Let's call them A and B. And then we want to find the shape of the curve that goes through the 2 points. So that'll be y of x. And we want to find the shape of the curve such that when we create a surface of revolution about the x-axis, Okay, so we want the shape of y of x such that this surface of this weird-looking thing is minimal. So it turns out this is a physical problem, right? It turns out that if the two circles here, if they were hoops, and you drew a soap bubble from one hoop to the other, the soap bubble will arrange itself so that the total surface area is minimal. So it's like actually has a real application. Okay, and it turns out that the solution of this particular curve occurs a lot in nature. It's called a catenary. The problem above problem 2.8 is specifically the catenary problem, but the solution will be the same here. Okay, so we need to write out now an equation for the total area of this object. So what we do is we can consider a small piece of the curve here. So let me take a little line element ds, and let me take a small element of the surface. And let me call that small surface dA. So the position of ds is y of x. So the area dA so it's the outer surface of a cylinder, right? The cylinder has a radius y of x, and it has a height ds. All right, so the area of the cylinder is 2 pi y times the height, which is ds. So the total area of our surface will be the integral from point A to point B of 2 pi y ds. And so this comes up in almost every single problem that you have the ds in it, and we already know now ad nauseum that we can write ds as 1 plus y prime squared square root dx. All right, so that's the hard part in this problem. So it's the physics. It set up the problem, and now we just apply the recipe to solve it. So the function L that we care about, you agree that the 2 pi really is not going to change the shape of the function, so the function L that we care about is y times 1 plus y prime squared. And so you'll note that this doesn't depend on x. And so we can use the standard simplified version. So it's y prime times diL by dy prime minus L equals a constant. All right, so we have y prime times diL by dy prime. So the y is a constant, and then diL by dy prime is going to give me a y primed and a 1 over square root of 1 plus y prime squared. And then the minus L term is minus y times 1 plus y prime squared, all square root. That must be equal to a constant. Alright, so now hopefully the math is getting a little bit familiar. So I can factor out the y. I'm going to put this all on the same denominator of 1 plus y prime squared And then the first term has a y prime squared, and the second term has the minus 1 minus y prime squared. That's equal to k. So the y prime squared and the parentheses cancel. And you square the thing. So I have y squared times 1 over 1 plus y prime squared equals k squared. Or y squared equals k squared times 1 plus y prime squared. Or y prime squared now is equal to 1 over k squared times y squared minus k squared. Or y primed is equal to 1 over k square root of y squared minus k squared. So this actually can be solved, although I wouldn't expect you to know how to do it. But let me show you how to do it. So I'll rewrite our equation. We have y prime equals 1 over k square root of y squared minus k. Alright, so that's the same as saying dy by dx equals 1 over k square root of y squared minus k squared, sorry. So that's like saying dx equals k times 1 over y squared minus k squared dy. If you want the technical term, this is solving by separation of variables. Right, this is a differential equation, and we're solving it using the method of separation of variables, since the x's and y's separate. So written like this, I can write this as an integral, right? So I have x is given by k times the integral of y squared minus k squared dy. And so that is actually something you can look up. And so that is k times a fun one, inverse hyperbolic cosine of y of k. And so I did a definite indefinite integral here, so when you integrate, you'll end up with some constant. Let's call it b, constant of integration. Remember, at the end of the problem, once you know the function y of x, you can go and evaluate the constants by requiring that the function go through the points. Okay, so now you can actually rearrange this a little bit, so I can have x minus b over k. Alright, that'll be inverse cosh of y over k. So you'll note the inconvenient thing is that we want y of x, and we found x of y in the line above, right? So it just happens that in this case, it's easy to invert because the solution to the integral was an inverse function. All right, so if I take cosh on both sides now, you can get that y equals k cosh, the hyperbolic cosine of x minus b over k. And then k and b are integration constants given by the usual condition that y at xa is equal to ya and y at xb is equal to yb. So I'll note for part B, I'm not going to tell you how to solve it, but you can get the answer in terms of x equals an integral of dy, but then that's too hard to solve. So the particular integral that you'll get in part B, yeah, I mean, if you write it out, it is solvable analytically, but it's like half a page long answer. Really, it adds nothing to do that. So don't worry about it. I'm going to tell you that in the notes, in the problem. Right, so any questions about that problem? So we've done almost all of the typical calculus of variation problems. The one that I didn't put in the problem set, it's just if you're interested. If you're interested, it's called Newton's problem. So it would define the curve like this. But when you do the volume of revolution, minimizes the total air resistance. And so the problem is to find the shape of the nose of an airplane. So that is again a calculus of variation problem where you write out the total wind resistance or the total force from the wind as an integral, and then you'll find the shape of the front of an airplane, which is kind of neat. And Newton was the first to do that. All right. So I think our time's up. The assignment is due next week, next Friday, and let me know if you have any questions. Thanks, everyone.